Okay, so the second part of the HL stuff, it focuses on like why compounds that contain these transition elements are colored, they're different colors. And so really it all goes back to that definition of being a transition element from last time, the fact that it has um, d orbitals that are unfilled. Okay, it has an incomplete d sublevel. And that's what allows it, because there's like an energy difference that's going on. And so um, they form different colors, and because we know from topic 2 that like white light's composed of all the wavelength of color of the visible spectrum. We have like red to violet. And so what happens is when light passes through a solution, for example, that has copper +2 ions, certain wavelengths of light are absorbed, and whatever is not absorbed is what is transmitted like for our eyes to see. And so anytime you have a complex ion that has copper +2, like this one, the solution to us, it looks blue to our eyes. And the reason is because if we look at what's being absorbed, so this graph right here is called an absorption spectrum. So this is showing us what wavelengths of light the substance is absorbing. And if you look, it peaks over here, and it's kind of in like the red and orange section. And so since it's mostly in the orange to red orange section, the wavelengths of light being absorbed are more in that red or red orange area, and therefore we see blue light transmitted. And so there is a color wheel that we're going to get to in a little bit that they're always complementary colors. So it's kind of like art class. When you have complementary colors, they relate that way. And so this is what it would actually look like in a lab. So any kind of solution that has copper-2 ions in it, it's always this blue color, because it's the complex ion with the copper-2 plus in it is causing that blue color, that bright blue color. And the reason, like atomic structure wise, the reason why this is happening is because it has that d sublevel that is not totally full. So for example, copper is going to have this one orbital that's unfilled in the d sublevel. So what happens is when the ligands bond to that copper ion to make the complex ion, there's some repulsion between the ligands and between the d orbitals. And so that repulsion, the ligands with their negative electron pair, it's repelling the electrons in these d orbitals, and it causes the 5 d orbitals to split. And so what happens is you get 2 up here that have higher energy, and then 3 down here that are lower energy. And that's kind of what it's summarizing here on the right side. And so what happens is, since 2 of them are higher, there's a difference in energy between them. And that amount of energy, that corresponds to a wavelength of visible light. And so just like when we did light calculations in topic 2, we calculated like the ionization energy, and that corresponded, to a wavelength of light and a frequency. It's kind of the same concept here, that this amount of energy corresponds to a certain frequency and a certain wavelength, and all the wavelengths fall in the visible light spectrum. And so that causes the solutions to look different colors. And so in the case of something with copper +2, it's going to be that blue color. Other substances are going to have other colors. And so this next section is talking about that when your electron transitions from that lower set of orbitals to the higher set of orbitals, it requires some energy. And so it has to absorb energy for that to happen. And so for copper, it absorbs kind of in this wavelength range, and that's corresponded, like I said, from that graph earlier, it's kind of the orange or the orange-red section. And so the complementary color of orange, which is blue, is what we see transmitted. And so down here, this little color wheel, you have your complementary colors. So like I said, it kind of looks like back when you were back in like art class, and they were like yellow and violet are complementary colors, and red and green are complementary colors. And so whatever light we see is what's being transmitted. It's actually the wavelengths of light, the opposite on this color wheel, that are actually being absorbed. So you can kind of color in your little wheel if you want to. You can color in a lot neater than what I'm doing. I'm just doing it really quickly. But just to help you kind of visually see, so then in this case, what's happening with copper is it's somewhere over 650 to 700. So it's kind of over in this range. And so we see usually mostly blue light from that one. And so basically, the summary of this is really because they have that incomplete D sublevel, when they come in contact with a ligand to create that complex ion in a solution, the d orbital split, and because there's an energy difference, the amount of energy that's between those two sets of sublevels or sets of orbitals causes you to observe one color of light or in the solution, because the opposite on this color wheel is what is being absorbed. So there are some things that can cause the color to change. So that's kind of the second section today, is what are the things that can cause the colors to be different. And really we're going to focus on kind of two of these more than the other two. But as it says like when the ligands bond, the repulsion between them causes the d orbitals to split, and that's what causes the different colors because of the complex ion. So the things that can affect the color is, what is the central metal ion? So like, is it copper? Is it cobalt? Is it iron? Okay, so what is the identity of the central metal ion? Because that's going to affect it, because different metals are going to have different, numbers of unpaired electrons and in the d orbitals and things like that. What's the oxidation state? So what charge does it have? Okay, Curtis, that's fine. You can watch the recording later if you need to. Okay, so oxidation state. So what's the charge on that central metal ion? Because for example, like copper 2+ is going to have one color, but copper 1+ might have a different color. Iron 2+ is going to be one color versus iron 3+ is going to be a different color. Okay. And then the identity of the ligands. So which are the ligands all the same? Like, are they all like water molecules? Are some of them cyanide or chloride or anything else from that list that we talked about last time with the ligands? And then the geometry of the complex ions. So what shape is it? Because that can affect the color as well. So those are the 4 factors that affect them. And we're going to look in a little more detail at a couple of them. So the oxidation state. So here's an example. Both of these have chromium in them as the central metal ion. But if you notice, this one is 2+, this one is 3+. And so since it's all water molecules that they're bonded to, which are water molecules are neutral. So in this case, that means that this one is chromium is going to have the same charge as the whole complex ion. So this is Cr2+, and this is Cr3+, because the metal will have the same charge as the complex ion. And so it says, deduce the oxidation state of the metal ion in each of the complex ion, explain why they're different colors. So I kind of just showed you the first part is, since the ligands are all 6 water molecules, which are neutral, they don't have a charge. The charge on our central metal ion would be the same as the whole complex ion. So one of them's 2, one of them's 3. And then for the explanation, okay, it kind of says right here, it says, as the oxidation state of the metal ion increases, the amount of splitting the d orbitals increases. Okay. And so this one over here is a +2, but this one was +3. So it's higher. It's got a higher oxidation state. And so it says a change in the oxidation of a state of chromium from 2 to 3 increases the difference in energy. Okay. And so if we go back to, if we think back to our electromagnetic spectrum from topic 2, higher energy is closer to violet. Okay. Lower energy. So that shows you why this one looks blue and this one looks more violet, because the wavelength of the light being absorbed decreases. Okay. And so if the wavelength is decreasing, then we're going to see something with higher energy, meaning more like the violet than the blue. Okay. So there's a couple more questions here, and it's kind of the same concept. They're obviously different colors, but your explanation is going to be similar. Okay. You will deduce what the charge is, and then based on which one has, a lower or a higher charge, that's going to correspond to, higher or lower energy, which will correspond to a longer or shorter wavelength, and therefore a different color on our spectrum. Okay. The other thing is the ligand can affect it. And so this last section is called the spectrochemical series. And what it does is it arranges all of the possible ligands that we can have in order of their ability to split the d orbitals in an octahedral complex ion. So over here with iodide, or iodide, because it's an ion, iodide has the lowest energy difference, because it says right here, the higher up in the series, the greater splitting of the d orbitals, and therefore the greatest energy difference. So carbon monoxide over here on the right side, carbon monoxide causes the largest energy difference. Okay, so highest energy difference is going to be something more that would be high energy, so that would be closer to like violet. Okay, so that's basically what it says here. Higher energy corresponds to shorter wavelength, and we should know from topic 2 that high energy and short wavelength is the violet side. The red side of the visible spectrum is the lower energy and the longer wavelengths. Okay, so on this list, carbon monoxide produces the greatest splitting, therefore the greatest energy difference. So we're going to see more like violet and blue violet over on that side. The side where you see like iodide and bromide and sulfide, that's probably going to be more like red or red orange. And so it'll kind of correspond that way as you go across. And so this last one, it says use the spectrochemical series to explain why the two complex ions below are different colors. Because if we look, they both have copper, okay? They both have a +2 charge, or 2+ charge, okay? And if you do the math, okay, then the coppers are both 2+, because over here, all 6 of the ligands are water. So that means this is Cu2+. And over here, 2 of them are water, but the other 4 are ammonia, NH3. And ammonia is also neutral. It does not have a charge. So this is still Cu2+. So the ion is the same metal, and it's the same oxidation state. So neither of those are different, okay? What's different here is the ligands. If we look on this one, all 6 of the ligands are water, but on this one over here, only 2 of them are water. The other 2 are, or the other 4, excuse me, are ammonia, okay? And so 2 waters, 4 ammonias. And if we look down here, the explanation, it says, because if we look at that spectrochemical series list, NH3 is further over to the right. And so that means I'm going to scroll back up here really quick just to kind of point this out. So here is NH3, ammonia, and then over here's water. So ammonia is further to the right. So that's where the greater splitting of the d orbitals happens, which causes a larger energy difference. And so on this example, because the one over here on the right has these 4 ammonias, that causes a greater splitting of the d orbitals, which means that this complex ion over here is going to have more energy. So it says more energy is absorbed by the electron's transitions. Therefore, the wavelength of light absorbed decreases, because higher energy means shorter wavelength. And so this one over here, it's going to have closer to red-orange light absorbed because it's got all the water molecules. The one that has the other one, it actually has yellow because it has 2 waters because they're a little lower, but it has 4 of the ammonias. And so that's what's absorbed. And so what we see transmitted is the complementary. So you would see like blue-green on this one, and you would see blue, but closer to the blue-violet section for that one being transmitted on that complementary color wheel. So that is pretty much it. Okay, you just have some practice exercise questions to answer. And what is going to happen next week is on Tuesday, I will be posting a review of all of 3/13 SL and HL material. And I'm probably going to post the test the same day. And I'm going to leave it open for you guys to do your review and your test on both Tuesday and Thursday. Since next week is the end of 6 weeks, I don't want to start anything new on Thursday. So I'm going to post the review. I might actually post the review over the weekend just so you guys can start working on it. But that'll be up. And then the test will be open on Tuesday along with the review. And it'll stay open until Friday night at 11:59 when the 6 weeks cutoff is. Okay. So you'll have class Tuesday and class Thursday next week to work on reviewing and testing. And we will not start new stuff until the next 6 weeks starts.
Okay.